अभी ज्वाइन பண்ணிட்டறா
சார் சார் ஜாயின் பண்றேன்னு இருக்கார் சார்.
ரைட் ஓகே ஓகே டன்
எஸ் சார்.
குட் ஆஃப்டர்நூன் சார்
Hello, good afternoon.
குட் ஆஃப்டர்நூன் சிவசங்கர்
சார் எஸ் சார்.
you talk to him and then you see that whether his presentation is going on. Give the approval to him or
Yes, sir. Okay.
screen share you approve.
Sir, you just share your screen, sir, so that we can check whether we can able to present it or not.
இல்லப்பா தம்பி see what I am telling நேரா நேரா நேராப்பா இல்ல இல்ல இதுல
Sir?
Yeah, can you see my screen right now?
yeah now you see
Yes, sir. Yes, sir. Okay, sir. Sir,
Just
okay,
one
sir.
second.
sir just you click the presentation whether it is working or not you just see or you run through your presentation. நீட்டா போங்க தேவையே தான் சர்வீஸ் ரோட்ல ரைட் it's
Okay, sir.
working yeah sir thank you
Sir,
you can close it sir we are expecting around 60 to 70 people so once some 40 people are joining then we will start the program. The agenda is like this. First we will welcome the gathering. Second is we will read your biodata. Third you can start the presentation. Then at the end of it we will see if any questions are there. We will ask the participants to ask the question. You have to answer and then finally we will thanks we will close. This is the program agenda, sir. Thank you. Is it any doubt or clarification is required?
No, thank you.
No. Okay. Thank you, sir. Thank you. We will wait for a few minutes, sir. Okay.
Okay.
MEIL அசோக் லேலண்ட் எல்லாரும் சொல்லிட்டியா
சார் பேசிட்டேன் சார் எல்லார்கிட்டயும்.
ரைட் இதுல பேசுன மெல்காஸ்ல பேசுனியா சக்திவேல் கிட்ட
சார் வெங்கடேசன் சார் கிட்ட பேசிட்டேன் சார். ஜாயின் பண்ணிருக்கார் சார். சக்திவேல் சாருக்கு மெசேஜ் அனுப்புறேன் சார். அவரு எடுக்கல சார் இன்னும்.
இப்போ போட்டு எடுப்பான் ஃப்ரீயா இருப்பான்.
சரிங்க சார். ஓகே சார்.
சார் பிரிட்ஜ் ஏறும்போது இறங்கும் போது லெஃப்ட்ல ஒரு ரோடு போயிடும். இது லெஃப்ட் நிமிஷம் ஆகும். இங்கே இருக்கலாமா? Dear fellow poultrymen, good afternoon to everyone. We will wait for some more participants to join, and we will start the meeting by 2:35 or little bit late. Kindly requesting everyone to be patient and wait for the session.
Team, can you hear us? Hello.
1 minute, sir. Sir, yes, sir. Welcome, Chairman. Namaskara, namaskara. We'll start the meeting in another 3 minutes, Chairman. Very good. So many people are sitting.
One thing is sitting, sir.
Good.
Thank you.
In another 2 minutes, we'll start the session.
You are traveling, sir?
Yeah, I am on travel in any way. We have to do the meeting. I stopped the vehicle.
Like to play. What is this? We can't now. This is ಈಗ ಅಲ್ಲಿ ಲೈಟ್ ಆಫ್ ಮಾಡಿ ಸಾಕು ಸ್ಕ್ರೀನ್ ಹತ್ರ ಆಫ್ ಮಾಡಿ ಉಲ್ಟಾ ಮಾಡ್ಕೊಂಡು ಇದೊಂದು ಹಾಕಿ ಅದು ಬೇಕು ಸ್ವಲ್ಪ ಇಲ್ಲಿ ಮೇಲೆ ಆಗ್ತದೆ ಸ್ಮಾರ್ಟ್ ಬಂದಿದೆ ಸ್ಮಾರ್ಟ್ ತಿವಾರಿ ನಾನು ಪಾರ್ಟಿಸಿಪೇಟ್ ಅಪ್ಪ
Good afternoon, fellow countrymen. It gives me immense pleasure to welcome all of you for this virtual meeting. This is our fourth meeting conducted by National Center for Skill Development. And next month also, fourth Friday, we are going to have meeting in the same 2:30 p.m. on economies of operations, on melting, and what are the advantages of using the latest technology in melting. The details will be given. Now, I welcome each and everyone for the active participation in this meeting. And some more people are yet to join. Let them join. In the meantime, it gives me great pleasure to introduce Anuj K. Tiwari, Assistant Professor, who received his PhD from Department of Mechanical Engineering at the University of Washington, Seattle in 2022, and BTech from IIT Guwahati in 2017. He worked as postdoctoral scholar from December 2022 to June 2023 in Boeing Advanced Research Center at University of Washington. He joined with IIT Madras as an assistant professor in mechanical engineering in July 2023. He works in mechatronics and controls, smart manufacturing, network dynamics, and advanced mobility systems. His current research focus is on distributed control of networked multi-agent systems with a particular emphasis on cohesive network transitions, where, where each agent in the network moves similarly. His research includes theoretical developments for consensus and synchronization of higher order agents in presence of delays and applications to cohesion in connected vehicles and advanced composite prototyping and flexible manufacturing. Apart from this, he has already taken classes for our AI program, residential program conducted at IIT Tirupati. He is a visiting faculty at IIT Tirupati. And with this, I am leaving the floor to Mr. Dr. Anuj K. Tiwari to proceed with his presentation. Thank you, sir. The floor is yours now.
Yeah, hello. Thank you so much for the introduction. I'll take it forward from here.
Yeah.
Okay.
Sir,
So
everybody,
I'll
is
just share
it
my.
audible to everyone? 1 minute, sir. Is it audible to everyone? Ganagappa, sir.
Yes, sir. Yes, sir.
Okay. So hopefully you can also see my screen, and I'll start the presentation now.
Yes, sir.
So again, thank you so much for the opportunity to speak to this particular group. Um, my research is, let's say, more on the controls and robotics side, where I interface with smart manufacturing systems, and I will try to highlight, let's say, certain areas related to industrial robots, material handling as one application, and what the approach that I take is using multiple robots. I'll try to motivate why multiple robots can be considered as an application. Um, so today's talk will be, I'll start with a brief overview of my research background. So my research background is in multi-agent robotics, where you don't just have one robotic system, but multiple robotic systems where they interact each other either through, let's say, sensing each other, or there are different robots communicating with each other in a warehouse, or multiple robots are handling the same object. So they are implicitly connected through the object, and then they form a network. Uh, I think someone has unmuted themselves. Maybe if they can mute, that would be better because there is an echo. Okay, yeah, thank you. So I also work on some robotics applications of flexible object transport. The main reason of working on multi-robot systems is it's scalable. That is, as the, let's say, the size of the object increases, you can increase the number of the robots. And it is also versatile. Depending on the shape or geometry of the object, you can place the robots in different configurations and still use the same multi-robot setup. So one of the applications that I looked at during my postdoc was advanced composite manufacturing, where we wanted to use this multi-robot networks for handling and also sort of molding these composite structures, which were still in their green state, that is, they were not cured yet. This was looked at for, let's say, decreasing custom fixture costs. And this work was done at Boeing Advanced Research Center. Uh, right now, we are trying to extend the same concepts here at IIT Madras in double-sided incremental sheet metal forming using multiple industrial robots. So what we have is we have two robots, Robot 1 and Robot 2. We have a fixture in which we fix our, let's say, the sheet metal on which we want to, let's say, form a certain shape, such as a cone, and there is a tool head attached at the end effector of one of the robots, uh, and that does the forming. Now this is single-sided forming. If there is a tool head on the other robot and it provides support from the other side, then it can also be developed into a double-sided incremental forming process. One certain example is shown here. So this is being done in collaboration with Professor Hariharan here at IIT Madras. Besides that, my long-term goal is to, let's say, bring industrial robots into automotive industry and some other applications such as welding. Uh, since I'm talking to people from foundry industry, robotics also has applications which can be beneficial for foundry industry. For instance, high temperature uh, molten metal dust noise fumes can make foundries unpleasant and hazardous places for people. So these are ideal locations for robots, which are, let's say, configured to work in these harsh environments. So adoption of robust heat resistance robots that can withstand the hostile environments and heavy workpieces of modern foundries may provide the flexibility needed to produce quality castings that meet each client's specification and reduce production costs, because the same system can be used to form multiple different uh, let's say castings. And that was one of the rationales behind using robots in even in double-sided incremental forming, because traditionally you will use a die and you can make a component by punching that die into a sheet metal, and usually that's pretty easy to control, easy to implement. But the thing is, like, it is not very cost effective when you are still in the prototyping phase, that is designing phase, where you want the same system to be able to make different shapes, but a single die can make a single shape. So you wanted a system which is efficient at prototyping different shapes using the same system, with using the same tool head, and it will decrease, let's say, your custom die costs, and you can make, let's say, different components using the same forming system. Uh, Heat resistant robots can be used to, let's say, handle many different applications within the foundry industry. It can be used for handling of molds, casting extraction operations, core assembly and setting, ladling of molten and cooling metal, and additional material removal tasks such as deburring, grinding, and polishing. Today, the research that I will present, which I have done, deals mainly with material handling, but similar concepts can be expanded to many different other, let's say, applications within the foundry industry. Now, as we know, when we talk about robots, we have to talk about types of robots. We can have robots which are, let's say, Cartesian robots, which only have degrees of freedom in X, Y, and Z domain. So these are called Cartesian robots. Articulated robots, which have serial joints. These are the most popular type of industrial robots we see. You can have SCARA robots, which can have, let's say, very high stiffness in one direction. So this can be used for operations where there is a high contact force at the end effector of the robot in one particular direction, but then it can move in a plane very easily. Delta robot, this is mainly used for handling, let's say, very delicate systems, mainly used in surgical robots. You can also have mobile robots where the robots are not fixed at a particular location but are mounted on mobile, let's say, systems, which can make it a mobile manipulator, which can be used many times in warehouses or factory floors for material handling. So we'll focus a little bit more on industrial robots. Then we will try to go a bit more deeper into the research that I have done in material transport using multi-robot networks. So as you have seen before, even robots can be of multiple different types. Cartesian robots, articulated robots, SCARA robots. There are more types of robots such as cylindrical robots and spherical robots. These are different joint configurations that you can have, and it makes the available space in which the robot can work, the workspace of the robot, different based on the different types of robots, and also certain features like certain high stiffness in certain directions compared to others. So let's try to see what are the different components that you need to think about when you're talking about using a robot in one of your own applications. So let us consider the following task, a very simple task of picking up an object from a tabletop and placing it at another place on the tabletop. So in order to implement this, let's say, task, the robot has to first determine the position of the object relative to the robot, that is relative to the base of the robot. For that, it can use some perception sensors such as vision. Then it needs to move the gripper, that is the tool at the end effector of the robot, which is the gripping tool, towards the object without colliding with the environment. Then that means it needs to plan the path of its tool and control the tool to follow that path. So planning and control are another component of industrial robotics. Then it needs to grasp the object. Let's say you have an off and on button, which can, uh, um, let's say this is a pneumatic gripper. It can turn on the pressure, turn off the pressure. So it will either close or open or change the direction of the pressure. Then after, let's say, grasping the object, you move the grasped object towards the desired position without colliding with the environment again, and then you release the object. Some industrial applications of industrial robots include assembly, drilling, riveting, etc. But they require precise control on even the contact force and not only on the trajectory of the end effector, where the robot has to come into physical contact with the environment. So for the robot manipulator to perform a task, for example, grasping, drilling, like we saw in the uh, previous slide, one needs to bring its end effector to an appropriate position or orientation. But when you look at a robot, you first see the joints, right? And joints have motors, and you can usually control only the motors. So motors are the actuators in this particular system. So um, you want to uh, do a task which is in the end effector domain. So that is the task space. But let's say uh, you can only control the angles. So you need to form a relationship on between the joint angles, that is joint angles of the robot, and the corresponding position or orientation that the end effector takes for those joint angles. So this is called forward kinematics. So this relationship between the joint angles of the robot and the end effector position is called forward kinematics, and the reverse is called inverse kinematics. Given a position or orientation of the end effector, what will be the joint angle that is that will give you that position or orientation of the end effector of the robot, that is called inverse kinematics. For instance, as an example, if you consider a two-link robot, that is, it only has two links like this and two joints here. There is a gripper here, and you want to control the location of the gripper XY in blue. Okay. Now each joint, okay. Now each joint is has an angle theta 1 and theta 2. So you can define x and y with respect to uh, the position of the first joint and position of the zero joint, where the zero joint is assumed to be at origin. And then you can write the location of x1, y1 with respect to origin like this, and x with respect to x1 like this. So that will give you a relationship between theta 1 and theta 2 and x and y. So that is the forward kinematics function that we are talking about. But as you can see, this is very non-linear. And if you have done any course in controls or systems, you know, nonlinear systems are very hard to control uh, because the mapping is not linear between theta 1, theta 2, and x and y. So this is not very easy to implement. Uh, Now, again, this is only a two-link robot. If you increase the number of degrees of freedom, let's say a general robot that you will get in your factory will be a 6 degree of freedom robot. That is, it will have 6 degrees of freedom, unlike this one, which only has two. If you exclude the angle that the gripper can have, the motion that the gripper can have, so this equation becomes even more complex. For that, we use the Jacobian matrix, which relates the rate of change of the end effector position to the rate of change of the angles of the joint motors. Uh, so this Jacobian is easier to uh, work with, because then it changes it into a, let's say, linearized system. Suppose that we want to place the gripper end effector at some x desired and y desired. The gripper orientation does not matter for now, so we don't take into account gripper orientation. We want to find the corresponding theta 1 and theta 2, which we represent as theta 1 star and theta 2 star, that achieve this end effector position for this two-link robot. And for that, you can try to solve it using the trigonometry. And so what we actually do is we take uh, uh, take square of this and add. So we see that, okay, somewhere it will be cos square theta 1 plus theta 2, sin square theta 1 plus theta 2. Then it will, let's say, uh, if you take d2 square common, then it will be sine square plus cos square. From trigonometric relations, you must remember sine square plus cos square equals 1. So that's how you can simplify out these non-linear trigonometric terms and only have linear terms, after which you can, uh, let's say, get theta 1. And similarly, you can get theta 2. So you can get theta 1 and theta 2, but again, these are not very easy things to find out. We can do it by hand for a two-link robot, but for a 6 degree of freedom robot, it is very hard to solve it by hand. So this is where we want to talk about configuration space and task space. Task space, like I defined before, is in the end effector space where you have to do the task, either drilling or polishing or material handling. You are only concerned with the end effector position. Whereas configuration space is the angle space of the robot, that is uh, theta 1, theta 2, and until theta 6 if you have 6 joints. So the set of all possible robot joint angles is referred to as the configuration space. So that is the different joint angles that the robot can take and denoted as, let's say, C. The dimension of the configuration space is then the number of robot joints. So a two-link robot will have a two-dimensional configuration space. The task space is defined with respect to the task at hand. So task space is not, let's say, fixed. It depends on the particular task that you want to do. Let me explain that through an example. To properly grasp an object, the end effector, so when the task is grasping an object, the end effector of the robot must be placed in a precise 3D position and 3D orientation. So your XYZ is fixed and your theta X, theta Y, and theta Z are fixed. In this case, the task space is the set of all desired 3D positions and orientations, which has dimension 6 because we have 3 translational coordinates and 3 rotational coordinates. So even your task space has 6 degrees of freedom. Whereas in a drilling task, one needs to place the tip of the drill bit at the desired location. So its XYZ is fixed. And to ensure that the drill bit is perpendicular to the drill surface, it has to take care of theta X and theta Y, 2 orientation coordinates. But then the drill is anyway rotating freely in theta Z. So the rotation around the surface normal is irrelevant. You can still drill for any theta Z value. So in this case, the task space dimension is 1 less than the previous example. That is, it only has 3 translational dimensions and 2 orientation dimensions. So that task dimension is 5 here. The reason we want to think about configuration space and task space when you're trying to use a robot is, in general, the dimension of the configuration space must be larger or equal to the dimension of the task space. Configuration space, in a way, is the ability of the robot. Task space, in a way, is the required degrees of freedom to do a task. If the ability of the robot is less than the, let's say, degrees of freedom to do a particular task, then that robot cannot fulfill that particular task. That is what is said here. So the ability of the robot should always be greater than the task space requirements. That is, configuration space dimensions must be larger or equal to the dimensions of the task space to ensure the existence of inverse kinematic solutions for a significant portion of the desired task values, so that you can find theta 1 to theta n values for an n degree of freedom robot given an XYZ location of the end effector. Now, when this happens, when you have more joint angles than, let's say, the dimension in your end effector space, then you can have multiple solutions which satisfy your task space condition. That is, let's say your condition is to keep the end effector of the two-link robot at this x value, x equals x desired, where you don't care about y. So your task space dimension is 1, but you have two options, theta 1 and theta 2, and different combinations of theta 1 and theta 2 can give you x equals x desired. All of them have the same x value but different y values, but you only want to control x. So it will have redundant solutions. So how do you pick one solution out of these? You can add some optimization conditions and try to fix these two theta values on top of it. But this is something that arises when your configuration space has more number of dimensions compared to the task space dimensions. We have seen in the inverse kinematic derivations for the planar 2 degree of freedom manipulator in the previous slides, where there were so many sine and cos terms, that the equations are quite complex, involving multiple inverse trigonometric functions, tan inverse, things like that, and validity conditions, like something should be less than 1 to be an argument of tan, right? For general 6 degree of freedom manipulators and 6 degree of freedom task spaces, which constitute the most common use of inverse kinematics, most of the task spaces are high dimensional, and most of the robots have 6 degree of freedom manipulators. The equations are even more difficult, and there are, in general, no closed form formula. So just like we were able to write the formula for θ1 star and θ2 star given an x desired and y desired in the two link robot case, that is not possible to be done in 6 degree of freedom robot. So there is no closed form formula. The task space inverse kinematic problem, that is given a desired task value, that is P, some position and orientation of your end effector. We need to find the configuration Q, that is the joint angles, so that the forward kinematics of Q equals P. So that when you put those angles in as the joint angles of your robot, your end effector achieves the desired task value P. This problem is very difficult since forward kinematics is in general a complex nonlinear function, which is difficult to invert. Because if for a given P, if you need to find Q, you in a way want to find the inverse of this function, right? Because then you can take Fk inverse on both sides, and then Q will be equals to Fk inverse P. But since for forward kinematics by itself is not linear and it is complex, you cannot really take the inverse that easily. That is why we use the Jacobian, which related Q dot to P dot, that is joint angle velocities to the end effector position velocities. So velocity space or differential inverse kinematics uses Jacobian. The velocity space or differential inverse kinematics problem is a little bit different from the inverse kinematics problem, where you can state it like this. Suppose that the robot is in a configuration Q, where the configuration Q signifies the joint angles of the robot. What joint angle velocity Q dot will achieve a given desired task space velocity P dot S. Okay. For that, you can use the Jacobian of the let's say robot at the particular configuration value Q, because it is a function of Q. And this is a linear mapping. So once you have written it like this, now you can write Q dot equals J inverse P dot, because J is a matrix and it becomes a constant when you set the values of Q. And this inverse is only possible when J is a square matrix, and it is a square matrix only when Q has the same dimension as P. That is, if P is 6-dimensional, Q should also be 6-dimensional. If the dimension of the configuration space is strictly larger than the dimension of the task space, that is the redundant case where there are multiple joint angles possible for the same end effector value, end effector position value, then we have multiple solutions, just like I showed before, of which an optimal solution can be chosen. For instance, if one is interested in the smallest joint angle velocity, then taking the pseudo inverse of J, you must have read about pseudo inverse in your mathematics classes, can be used to find out Q dot given a P dot. And all these computations are taken care for you. Like Rapid is a programming language developed by ABB robots for their own robots. Similarly, Fanuc has Carol, Kuka has KRL, and things like that. Universal robots can be controlled through Robotike. So all of these have libraries, and usually, let's say in ABB, if you want to move the robot, you have to use just a function move L, provide the end effector position where you want it to go, and the program will itself calculate what should be the joint angles it should take to reach that particular position. Okay, but it is good to know these under the hood operations also, broadly, like what's happening. Now, so far, we have looked at, let's say, robotic applications where the end effector is free. Let's say you want to just track a trajectory with the end effector, which is good for certain applications like inspection applications. You can mount, let's say, a camera at the end effector of a robot. And in order to, let's say, uh, uh, inspect a particular component, you have some desired trajectory. And according to that trajectory, you can find through inverse kinematics the position, uh, the angular position encoders at the joints, at the joint level, and control the robot. But a robot end effector may interact with its environment. That is, it might be modifying the state of the environment. That is, in pick and place operation, it is changing the location of, let's say, certain objects, or exchanging forces. Example, assembly operations where, let's say, in a screwing task, you have to provide a torque to screw and assemble certain components. Surface finishing tasks, let's say, you have polishing, or you have material removal process. So in those cases, it is exchanging forces with respect to the external environment, where many a times the external environment is the workpiece. Just like the sheet metal forming example I showed earlier. Uh, in order to do this, let's say, interaction with the environment, where the environment can be a workpiece, robot end effector may be equipped with devices so that they can sort of control the forces. One way of controlling the force is passively. That is, you have certain devices mounted on the end effector which comply with the generalized forces applied at the tool center point. Uh, so this is passive sort of control. You can also go active control, where robot position is controlled using, let's say, some sort of feedback of the forces at the end effector, typically measured by a force torque sensor, 6-axis force torque sensor, such as the one supplied by ATI. Uh, there are different types of controls that you can do to control the active interaction between robot and end effector. For instance, admittance control, stiffness or compliance control, and impedance control. In order to, let's say, control the position of the robot with some force feedback, there are many different approaches that are available to control the actuations in the joints of the robot. One such approach, a very simple approach, is limited sequence control. It is implemented by setting limits or mechanical stops at each joint, which you many times do when you set up a new industrial robot, especially if it is a huge robot like a metal forming robot. You usually have mechanical locks on the joint, so that in no operational condition can the joint value exceed a certain value, because then the robot might not be safe. It might hit the roof or a beam or something like that. So you can have mechanical stops for each joint. And then you sequence the actuation of the joints to accomplish the task. So first you move joint 1, then joint 2, joint 3, joint 4. So this is how you do limited sequence control of the joints. There in step 1, you move joint 1, step 2, you move joint 2, things like that. Playback with point-to-point control, where, let's say, you move the robot either physically or in case of a collaborative robot. But if it is not a collaborative robot, you can teleoperate it using a pendant or a teleoperation device, um, and move it from A to uh, B, C, D, E, and F, and then ask it to repeat. So while you're moving it, either through teleoperation or physically interacting with the manipulator, if it is a cobot, uh, it is recording the joint angles. So it is creating a history of joint angles. And later on, when you ask it to play back the same trajectory in the end effector, all it does is it plays back the joint angles history, and then it will move along the same sequence of motion. So the earlier one was point-to-point control, where the end effector being at a particular point was only required at the ends of these, let's say, trajectories. So in between, the interpolation can be anything. But many a times you also want to control the continuous path in between the point-to-point control. So in continuous path systems, not only the XYZ axis are controlled, but the velocities dx by dt, dy by dt, and dc by dt are also controlled simultaneously to achieve the specified linear or curvilinear path between the 2 points that you have, and which is applicable. Let's say you want to do some sealant operation or something like that, sealant application in certain places in your workpiece. And intelligent control is a fourth type of control, which provides the capacity to interact with its environment. It provides the robot the capacity to interact with its environment, make decisions when things go wrong. That is, it has some decision-making capability locally during the work cycle, um, communicate with humans, make computations during the motion cycle, and respond to advanced sensor inputs such as machine vision. So this is the most advanced type of control, that is intelligent control. In order to interact with the environment, there should be some sort of a mechanical system at the end effector of the robot. where it differs for different applications, such as mechanical grippers. These are some of the most common ones where you have two jaws, which can be actuated, let's say pneumatically or electrically, which are used to close on a particular work part and then either move it or modify it. Vacuum grippers, let's say, used extensively in sheet metal industry, in which suction cups are used to hold flat sheet metals and move them from one part to another. You can also use magnetized devices for ferrous parts or adhesive devices which use an adhesive substance to hold a flexible material such as a flat fabric. You can also use simple mechanical devices like hooks or screws. Uh, a robot program. So many a times you don't want to just teach a robot a trajectory using one of these control types, but you want it to have, let's say, some sort of intelligent control. So in order to implement any intelligent control, you have to do robot programming. That is, you have to write a program or develop a program and put it on a robot. For these, three programming methods can be used. Like these are different methods which can be distinguished into three different methods. Lead through program. It can either be manual or automatic. One example of lead through program is given here, where you manually move the robot. Since it's a cobot, it is safe to do this. You press a key to close the gripper because that is a separate control. And then you play back the motion. That is, while you were doing that, the robot was recording the joint trajectories and it will end up at the same location. And then it will close and grab the object. So like this is lead through programming and this is manual, but this same thing can be done automatically where you have some sort of a program that teaches it. But these things can only be done for very simple operations, such as uh, pick up, place, things like that. When you have complex operations like sheet metal forming, uh, where I think someone again unmuted themselves. Okay. So this is only possible in very simple examples, but in certain examples, let's say you want to control a certain level of force. You want to do some force control so that when your end effector with the tool is in contact with the sheet metal, it applies a certain level of normal force. Now, if you over push, normal force will increase. If you under push, your normal force will decrease. So you have to do the position control of the robot end effector with the force feedback. In order to implement, let's say, a programming logic like that, you have to write a code for it and then put it onto the robot. And for that, there are several interfaces which are provided. Many of the robot companies will provide those interfaces for themselves, and they have different programming languages, but usually under the hood all of them are C++ codes, because C++ codes are the most real time in execution, but they provide you wrappers around those C++ programs, and then you can use them to control your robot. Offline programming is one way of, let's say, checking the code on the robot without stopping the robot, that is at a remote computer terminal, and download to the robot controller for execution without later on without interrupting production. So let's say if you have a robot in production, but you want to improve the execution of such some manufacturing process through the robot, you can develop the code offline and maybe test it out in a simulation, and then flash that code to the robot controller for execution without interrupting the production. A robot studio is a suite provided by ABB, which is very well suited for that, because uh, a simulation will perform almost exactly as how your actual robot will perform once you use the same code on the simulation and the robot. So testing your code on a simulation is very effective in certain in such realistic simulators. Also, that is why ABB is mostly used in most precision, uh, let's say, environments. Also, you can have a digital twin of your robotic manufacturing system so that you can control the robot and detect anything that is going on in the actual system by comparing it with the simulation system, how it should happen ideally and how it is actually happening. And if there are any deviations, you can implement some control here to bring it back to the nominal state. So most of the current applications of industrial robots are in manufacturing. The applications can be classified into many different categories: material handling, processing operations, assembly and inspection, and things like that. And today I'll be mainly talking about material handling as one application. So uh, also, before I go into material handling, I also want to talk about collaborative robots. There are many cases where a robot by itself cannot execute a task, just due to the nature of the complexity of the particular task. So you have to have a human overseeing the operation, and many times a human in close quarters to the robot. So in that case, for safety of the robots should have for safety of the human, the robot should be collaborative. Uh, that is, uh, they should be safe to work around humans. They should detect collisions and not apply more force than required in case of those collisions, so to minimize injury risks to the operator. Now, when you're talking about this sort of compliance, you are talking about, let's say, how you can interact with your environment and do some sort of force control. And this is where I want to uh, introduce my research topic on material handling, where the material that we handle is flexible. As I said, the application that we were looking at is composite structures, where the composite structures have not been cured yet, so they are still flexible. And these composite structures could be as long as 60 feet. So at that length scale, and other dimensions are much smaller than the length, then it is actually just like a ribbon or a noodle. It's very flexible. So you should be able to transport, first of all, such structures across factory floor for different operations without deforming them. Because in aerospace industry, the margins are very tight, and you cannot use structures with any residual stresses or strains. So uh, we wanted to develop a multi-robot system to transport such big objects while the object was very flexible, uh, and to minimize deformation in the object. So we wanted to use, let's say, force sensors at the end effector of the forces to reduce the deformation of flexible structures when we are transporting them collaboratively using multiple robots. So our approach is shown on the right hand side, which I will derive in the next few slides. So let's talk about uh, deformable material transport using multi-robot networks, which is the flexible object transport application in my research. Before we go further, let's take talk about some background on object transport. So using multiple robots to transport object can be uh, has been taken as an inspiration from natural systems, where several ants are able to transport objects much bigger than themselves, and some of them even flexible, like um, together collaboratively without, let's say, explicitly communicating with each other. So they are just doing local vibration control and achieving the transport of the objects, such as Cheerio, which is a cereal here. Taking a look at this, let's say, natural system, people have been trying to develop multi-robot systems to do similar transport in engineered systems. Um, Such as this 2016 paper here, where each robot has certain wheels for transport, but also some way of connecting with an object and some force torque sensor here to detect the local forces. So this is a nature inspired system. In the context of using multiple robots for transporting, let's say, bigger objects than themselves, the approach can be distinguished into a centralized approach and a decentralized approach. Centralized approach means something like this. So let's say you have multiple robots transporting the object, and all of the robots are aware of the, let's say, the trajectory to follow to transport the object. That is where to take the object. They have the desired trajectory information. That is, let's say there is a virtual source, which might be another virtual robot, and it is telling all the robots where to go. Whereas a decentralized approach is something where only one of the robot or a few of the robots, which are called leader robots, know where to take the object, and the follower robots only do local force control to move the object. So this is a decentralized approach. There is no central controller, but each robot has its local control, which they're following using only local measurements. And one of the robots is a leader, which has some extra information. Now, the centralized approach is ideal for trajectory tracking. Let's say if the trajectory that you want the multi-robot system to follow, all the robots in the system already know that trajectory, then they can follow it very efficiently. But it requires accurate models of transport to prescribe the desired trajectory, and it needs sufficient communication bandwidth. On the other hand, in decentralized approach, since each robot is doing only local force control, they have the possibility of not moving, let's say, cohesively, and uh, either expanding or deforming the object that they are carrying, especially when the object is flexible, which is the application we were looking at. So it can lead to damage of the objects, but it has some good aspects, such as it is robust to failure of agents since it is not centralized control. It is scalable. It can be scaled up very easily because each robot is using only local sensor information. So let's say if the object size is much larger, you can just increase the number of robots, and you won't have to worry about additional communication channels. And it is versatile to different tasks. So that was the inspiration of using multiple robots to do the handling of composite structures in aerospace industry. So in order to look at the current limitation of deformation in the objects when you carry it, we just show a very simple simulation here, where let's say these square boxes shown here represent the robots. The red box represents, let's say, the leader robot, and the blue box represents the follower robots. The black line here, let's say, it represents the flexible object. And let's say each robot has a state, where the state is the Y position of the robot. Let's say the leader robot, that is the robot box in red, knows that, okay, you have to take the flexible object to some Y position YD, okay, Y desired. But the follower robots only have local force sensors, and they can only sense the local deformation, because local force will be non-zero only when there will be local deformation, and they react to it to move to reduce it to zero. For that, the leader's update can be written something like this. So leader's position at the next time step m plus 1 is the leader's position at the previous time step m, and it is updated by this term where it is minus gamma times f1m. So it also has some local force sensor, and it is trying to reduce the local force, but at the same time it is trying to track desired position yd, and only y1 has leader robot has the desired position. And the followers update law can be written as y sub k for the kth follower, where k goes from 2, 3 to 4, uh, where ykm plus 1 equals yk at time instant m minus gamma fkm. So it has some sensor which is giving you the local force value fk, and it is just moving in the direction where it reduces the force. So if you simulate this simple mathematical system, you can see that during the transport, the black line is deforming. That is, it is losing its initial shape, but it comes back to its shape, assuming, let's say, it is still in its um, uh, it has not entered the plastic region. Now here we can look at two metrics, that is transport time and deformation. So we want to reduce deformation, but at the same time, we want to also complete the transportation task as fast as possible. But let's say here in this control law, all you have access to is this control gain gamma. So here you can see that if you increase the control gain gamma, you are able to transport it in a shorter amount of time, but your deformation increases, right? So if you want to decrease deformation, you will need to increase your transport time, which makes sense. If you are moving slowly, transporting a flexible object, you will deform it lower, right? The deformation will be lower, which makes sense. So the research question that you want to answer is that there is a trade-off between transport time and deformation. But the challenge is that reducing deformation requires increasing transport time. So the main question is, can we reduce deformation during transition in a decentralized manner that is only using local force values without increasing transport time? So in order to do that, we can borrow some ideas from the optimization literature, where we can try to see how accelerated methods can be used to reduce deformation. So for that, you can write again the transport equations of the simple system that I showed in simulation, but we had an exact physical system also built up, custom built robots with load cells to get like local force sensor values, and flexible coil to represent the flexible object that we're transporting. And then we can write the equations of motion as a network update law, where the state of the network is the state of the all the four robots in the multi-robot system. And the update law can be written in a matrix form, where capital K here represents the stiffness matrix, which in graph theory, where you can model this multi-robot system as an interconnected graph, represents the interconnectivity between the different agents. So the stiffness matrix looks something like this, uh, where the force feedback will be K times Y when deformation is small. So here in this slide, we started with the update equation as in simulation, but for a physical system, and we rewrote it as a network-based update law. The main idea is the network-based update law can be written as a gradient descent on a potential function. So you must have read about gradient descent algorithms in machine learning. Similar concept is here, but here the gradient descent is being done in a potential function, where the potential function uh, models the deformation in the object, where phi is the network potential function given by this. Accelerated approaches, that is descending on the potential function faster, we can potentially reduce the deformation, which involves adding these extra terms here. So these terms are called the delayed feedback term in blue and the momentum term in orange. So this is the accelerated gradient based update law. How do you select these parameters? You select it for stability. You can prove stability by looking at the spectral radius of this big A matrix, which you can get by making consecutive time instances of Y state vector and putting that as a big state vector and writing the discrete update law. And it is only stable if the spectral radius, that is the largest eigenvalue of this big A matrix, is less than 1. Okay. So using that, you can find the update parameters gamma, beta 1, and beta 2. And then you can use that for the accelerated gradient based approach. So we evaluated it experimentally on this system that we built ourselves. So the desired trajectory that was given to the leader robot, which is only available to the leader robot, was a slow ramp in position. That is, the slope was 3 centimeter per second. That is a constant speed to reach 50 centimeter. And the initial position was 0 centimeter. And the metric was what is the difference between the position of the first robot and the last robot, that is y1 minus y4. Because usually this is the last robot to react based on the force sensor reading. And these are the parameters that were selected. And they were selected for the same transport time between the standard approach and the accelerated approach for fairness. And then we show the experimental results. Here you can see that using the same force sensor value, the deformation on the right hand side, which is the accelerated approach, is smaller than the deformation in the left-hand side, which is just like standard approach. So we are able to reduce deformation somewhat. And this is a comparison between simulation and experiment. So even though the simulation that we performed didn't account for friction, didn't account for many of the slipping things that happen in real life, even then it was a good approximation of what we saw in experiments. So the controller that we built was able to show 61% reduction in deformation of flexible object when you are transporting it linearly. There are still some issues with the accelerated method where it has to be optimized for a particular desired trajectory. So can we do better? So can we go beyond the accelerated approach? So we developed something called delayed self-reinforcement, where I won't go through the derivation again because it is, I think, too much mathematics for this crowd. Uh, so the DSR-based approach, again, we want to select parameters for stability, but this is another approach that we developed where uh, even though the video is moving in steps, it is actually continuous. So you can see that now the flexible object remains approximately horizontally until finally the leader robot reaches 50 centimeter, it stops, and the force sensor value is now in, let's say, noise region. So the small motion that you see is due to the noise in the force sensor reading. But we were able to, let's say, reduce the deformation significantly. This is simulation and this is experiment. So the experiment is matching simulation very well. We were able to show even more reduction using the DSR-based method, which is 85%. The DSR method reduces deformation significantly during transition. But so far we have only shown 1D translation. In any transport task, you will eventually want to do 2D transportation. So that for that, the approach that we developed in DSR is not directly applicable. So we made some changes in terms of how to uh, uh, do orientation change while doing the transport task and still develop a method that reduces deformation. So we developed a DSR based approach for planar transport where you can transport it in a plane with orientation change also. The main challenge again was to select parameters while maintaining stability of the system. We used a result from 1970 from the source paper to prove frozen time stability and then slowly varying time stability using Lyapunov based method. But after that, we get a way of selecting our parameters. And then we again do our experimental test on the same system, where now instead of moving straight, we are moving in a curved trajectory. So again, the leader robot has the desired trajectory and the follower robots use local force sensor values, where the force sensor is again changed to get Fx and Fy and not just F in the vertical direction. And we were able to see significant reduction using the DSR-based approach for planar transport uh, uh, compared to the standard approach, approximately 72% reduction. But so far, we have shown results only on, let's say, custom robots. How does it perform on industrial robots? Uh, that is something that we showed here, where again, there is a leader robot here, which initiates a circular trajectory. So it moves in a circular fashion. And the follower robots sense local non-zero force readings using 6-axis force torque sensors and move to reduce the force value. So we have 3 follower robots. So if I pause it here, these are clamps to add the force torque sensor. And after the force torque sensor, we have the pneumatic grippers, where the jaws of the pneumatic grippers were 3D printed. And this is a flexible object. We have a tape on the top just to show when it deforms, it's easier to see with the tape. And then we overlay a red circle, which denotes the undeformed shape. So if the blue tape matches with the red circle, then it is not deformed. If it is very different, then the deformation is larger. And as you can see, the max deformation with the proposed approach is approximately 80% smaller than the standard approach. So we were able to show that the same approach that we developed using very simple model mathematically, tested it on custom built robots, let's say use on small experiments. But then we were able to show that it transfers directly to industrial robots, and you can see the significant reduction in deformation of the flexible object during the manipulation or during the transport task. So we are looking at approaches of further reducing deformation. But I think I'll just skip that. So we are looking at the aspects of delay. We are looking at current efforts are integrating complex robot dynamics with actuator delays into the uh, theoretical development, dynamic and static obstacle avoidance, and human teleoperated multi-robot network. I also use the multi-robot control, let's say that I developed for platooning in multiple vehicles, and also for coordinating multiple warehouse robots for inventory management and warehouse management. So we have a project from Walmart, which is running right now, where we are trying to develop reinforcement learning based approach for coordinating multiple robots in warehouse environments. So uh, again, you can see that this swarming multi-agent systems can be seen very easily in nature. So there were some people who presented their work in Nature Physics in 2014 who saw a flock of birds doing a turning maneuver very cohesively without deforming. Uh, and they saw that the turning maneuver was initiated by a few flock of birds, and then the information propagated through the system. And when we applied our control law that we developed for a very different application for flexible object transport in simulation to swarm systems, we saw that it was able to predict the low distortion information propagation in even in natural flocks. So whatever was observed empirically, it actually was working like that, even in uh, uh, even in swarm systems. So uh, my research can be, let's say, uh, looked at as working in the area of control of network dynamical systems with applications in robotics and controls. One of the applications I look at is smart manufacturing, which is the main application I presented today. But I also work on warehouse control and connected vehicles. Uh, and yeah, so this will be the end of my presentation. Uh, and my email is here in case you have any questions. And I think I can also take some questions right now. So thank you so much for listening to my presentation.
Uh, Good afternoon, fellow foundrymen. Is there any questions are there? Kindly raise your hands and you proceed. Shankar, anybody is asking?
Sir, sir, no, sir.
No.
Sir, Bhushan is there.
Yeah, please.
Thank you very much for insight. It was quite, in-depth and quite technical as well. My question would be like having this know-how with the current foundries, mainly challenges they are facing into the fettling areas to reduce the fettling time and so on and so forth. I mean, what level they can use it in the simplified by mean of because robotics has its own cost and cost. So, having said that, what do you see how Indian foundries can be impacted or how it should be moving forward using this kind of tools for reducing fettling time and so on and so forth?
I was also involved in a workshop that was conducted at IIT Tirupati, where several foundry men were, uh, let's say, uh, present, and they are already, some of them are already using these, let's say, uh, these robots, but only in material handling systems, mainly in material handling systems, and they were able to see, let's say, significant improvements in the cycle time of a particular process. Now, fettling, that is uh, like some finishing process for removing extra material, uh, that is a process which is harder to control because then the robot has to, let's say, interact with the surface to remove the extra material from steel castings. So those have to be trained. Either you develop a specific controller for that. For that, you need a certain level of know-how. So collaborating with universities, you can maybe try to automate such processes. But when you buy an industrial robot from a vendor, the so the level of support that you will get, you can only easily automate only, let's say, pick and place operations, something like that, which can potentially help you, let's move heavy, let's say, equipments or heavy tools from one place to another in a faster fashion, reducing the overall cycle time, which is one of the applications that people were looking at already in some of the foundries. Uh, but let's say when you want to automate certain operations like fettling, then you need a bit of a more deeper, let's say, dive into the technology and develop, let's say, the the corresponding tool. And once you have the corresponding tool, which you will be mounting on the end effector of the robot, how do you control the robot to implement the process? Now that is an R&D problem, which I think most R&Ds cannot do in-house. So let's say developing these technologies or these processes through robots in collaboration with universities, and then slowly adopting it. I think that is the way to go. But in certain cases like pick and place, I think people are already using it with some success in reducing the cycle time of the operations.
Okay, thank you.
Sir, anybody have any doubts, sir? Sir, sir, please wait, sir. Dayalan sir is joining, sir. Sir, Anuj, sir.
Yeah, hello.
Yeah, sir, I think Dayalan sir is having some network issue.
Okay.
So he can't able to join. I thank you for every members to attend this program and taken the valuable insights of the kinematics of the robotics and the programs went well. I thanks one and all, sir. I think Dayalan sir is having some issue in joining, sir. That's why, sir.
Okay, no problem. Yeah, thank you so much for
Yeah,
having me.
yes. Yes, sir. Yes, sir. Thank you, sir.
Thank you.
And thank you, members, for joining the program.
Thank you, sir.
Thank you.